In 1905, a young physicist named Albert Einstein published a groundbreaking theory that would forever change our understanding of the universe: the special theory of relativity. This revolutionary theory challenged the long-held Newtonian view of a static and absolute space and time, proposing instead that these concepts are relative, dependent on the observer's motion. Einstein's theory, with its elegant mathematics and profound implications, laid the foundation for modern physics and revolutionized our understanding of gravity, space, and time. Before Einstein, physicists believed that space and time were absolute and unchanging, a rigid framework against which all motion could be measured. However, this view was challenged by experiments that failed to detect a hypothetical medium called luminiferous ether, through which light was thought to propagate. Einstein's genius was to discard the ether concept and propose that the speed of light is constant, independent of the motion of the source or observer. This radical idea had profound consequences, leading to the realization that time and space are not absolute but are intertwined and relative to the observer's frame of reference. One of the most mind-boggling consequences of special relativity is the dilation of time, the notion that time slows down for objects in motion relative to a stationary observer. This phenomenon, though counterintuitive, has been experimentally verified and has significant implications for our understanding of the universe. Einstein's special relativity, with its profound implications for the nature of space and time, marked a paradigm shift in physics. It paved the way for the development of general relativity, which extended these concepts to include gravity, and continues to shape our understanding of the cosmos and the fundamental laws that govern it. At the heart of Einstein's special relativity lie two fundamental postulates that challenge the classical Newtonian view of the universe. These postulates, seemingly simple yet profound in their implications, serve as the cornerstones upon which this revolutionary theory is built. Understanding these postulates is crucial to grasping the essence of special relativity and its consequences for our perception of space and time. The first postulate states that the laws of physics are the same for all observers in uniform motion. This means that the fundamental laws governing the behavior of the universe are independent of the observer's velocity. Whether you are standing still, walking down the street, or traveling at a significant fraction of the speed of light, the laws of physics remain consistent. This principle of relativity, extending back to Galileo, asserts that no one inertial frame of reference is privileged over another. The second postulate, perhaps the more revolutionary of the two, declares that the speed of light in a vacuum is constant for all observers, regardless of the motion of the light source or the observer. This statement has profound implications, challenging the classical notion of relative velocities, where an observer's speed adds to or subtracts from the speed of a moving object. Einstein asserted that the speed of light, approximately 299,792,458 meters per second, is an absolute constant, an unsurpassable speed limit in the universe. These two postulates, seemingly simple on the surface, form the bedrock of special relativity. They have led to groundbreaking insights into the nature of space and time, challenging our intuition and revolutionizing our understanding of the universe. One of the most mind-boggling consequences of Einstein's special theory of relativity is the concept of time dilation. Time is not absolute but is relative to the observer's frame of reference. This means that time can pass at different rates for observers moving at different speeds relative to one another. This concept, though counterintuitive to our everyday experience, has been experimentally verified and has significant implications for our understanding of the universe. Imagine two identical clocks, one remaining stationary on Earth and the other placed on a spaceship traveling at a significant fraction of the speed of light. According to special relativity, time will pass more slowly for the clock on the moving spaceship compared to the clock on Earth. This difference in the passage of time is not due to any mechanical malfunction of the clocks, but rather a fundamental consequence of the nature of space and time. A classic thought experiment illustrating time dilation is the twin paradox. Suppose one twin embarks on a journey into space at a high speed, while the other twin remains on Earth. According to special relativity, the twin on the spaceship will age slower than the twin on Earth. Upon returning from the journey, the traveling twin would find their Earth-bound sibling significantly older. Though seemingly paradoxical, This difference in aging is a direct consequence of time dilation, a real phenomenon predicted by special relativity. Experiments with atomic clocks have confirmed this effect, with clocks flown at high speeds showing a slight but measurable time difference compared to synchronized clocks on the ground. This concept of time dilation, though challenging our everyday intuition, is a fundamental aspect of the universe we live in. Section 4: Length contraction, shrinking at the limits. Alright, let's dive into the fascinating interplay of mass and energy.